In this video, we will learn, in theory at least, about how to find the center of gravity for a rigid body. So let's imagine this pile of sand is tightly glued together. So I formatted the picture to reflect that, and now it has become a solid, undeformable rigid body. And it is still made up of infinite number of particles with differential weight dW distributed through its volume. We can use a concentrated weight force W to replace this distributed load, and W equals to the integration of the differential weight dW. Therefore, the two load systems have the same magnitude of force. But this is not enough. They also have to create the same moment about any arbitrary axis. Therefore, this concentrated weight force must be positioned at a specified location to be able to fully replace the distributed load as its equivalent system. And this specified location is known as the center of gravity for this body, represented by point G. The total moment of the original distributed load summarized about any axis passing through this point is 0. So why do we want to find the center of gravity? As you can see, if we do know its location, in some cases it is convenient for us to replace a rigid body by a particle located at this point. For a rigid body, in general near-Earth situation, when the gravitational acceleration g can be considered as a constant about 9.81 meters per second squared as we know it, the center of gravity is the same point of center of mass for this rigid body. And it is a unique point fixed in relation to this body, which means that if you move the body around or rotate it, the center of gravity stays at the same point relative to the body. Please be noted that this point could be outside of the physical body. For example, for a boomerang, you can imagine its mass center being outside of its body. And also, when a rigid body has uniform density, the center of mass, which is also the center of gravity, superimposes with the centroid, which is the geometric center of the body. So how do we find this center of gravity? Since location is always described in relation, we need to first put the rigid body into a fixed coordinate system. And again, the body is made up of infinite number of particles with differential weight dW. And we first want to find out the resultant moment caused by this distributed load about the x-axis. So we start with an arbitrary particle located at the arbitrary position given by the coordinates x, y, z, and the moment caused by its weight dW about the x-axis is calculated by dW times the moment arm, the perpendicular distance to the xz plane. In this case, coordinate y. For convenience, let's set a positive moment to be clockwise. Therefore, we have dmx equals to y times dW. And therefore, the resultant moment about the x-axis is the integration of dmx, or the integration of y dW. And if we replace this distributed load by the concentrated force, which equals to the integration of dW in magnitude, and it is positioned at the center of gravity with coordinates x bar, y bar, and z bar, the force W needs to produce the same amount of moment about the x-axis, which is the moment arm y bar times integration of dW. By comparison of these two equations, we know that y bar can be determined by the integration of y times dW divided by the integration of dW. And similarly, we want to find the resultant moment of the distributed load about the y-axis. We do so by, again, picking an arbitrary particle located at the location xyz. Its moment about the y-axis equals to its weight dW multiplied by the moment arm, the distance to the yz plane, x. Therefore, the resultant moment about the y-axis is the integration of dmy, or the integration of x dW. Then again, the concentrated force W needs to produce the same amount of moment about the y-axis, which is the moment arm x bar times integration of dW. By comparison of these two equations, we know that x bar must equals to the integration of x times dW divided by the integration of dW. But how do we determine z bar? Since the weight forces are parallel to the z-axis, it doesn't seem that we can use the same approach to determine the z-coordinate of the center of gravity. However, don't forget we said earlier that the location of the center of gravity is a fixed point in relation to the body, no matter how the body moves or rotates. Therefore, let's imagine the body is fixed in this coordinate system and rotate the body and the coordinate system all together. And now the system has been rotated. And of course, now the weight force should still be downwards, like this. And now for an arbitrary particle with weight dW at location xyz, its moment about the x-axis equals to dW multiplied by its moment arm, z, and the resultant moment about the x-axis is the integration of z dW. And similarly, the resultant moment caused by the concentrated force W about the x-axis equals to the moment arm z bar times the integration of dW. Once again, by comparison, z bar must equals to the integration of z times dw divided by the integration of dw. Therefore, as a summary, now we know how to theoretically determine the coordinates x bar, y bar, and z bar for the location of the center of gravity for a rigid body. In these equations, x, y, and z represent the coordinates of each particle that belongs to this rigid body. You might wonder, how is it possible? Luckily, as we will learn, center of gravity can be simplified to the centroid of a volume or even a centroid of an area. And also, bodies with complicated shapes can often be simplified as the combination of several common shapes for which the centroids can be determined much more easily.